Hello and welcome. In this video, I'll be solving a couple of problems for the topic electrostatics, right? So if you are new to this channel, please hit the like and subscribe button and just to show support to the family, right? So let's get straight into the first question here. It's question 7. So of course you can see here that we have a metal sphere X, which is the sphere, right? It's metal sphere X, and then it has got the amount of charge there. So the amount of charge it's given, it's 5 nanocoulombs, and then it's being suspended, you see there, right? So obviously I would advise that you read all the information here, right, yourself. So we have another metal sphere Y, which is here, right? So this is the amount of charge. It's a negative charge, so it's negative 8 nanocoulombs, right? So we see again that we have some information there, right, that this charge is brought closer to sphere X until their centers are 20 millimeters apart, right? So this is the distance between the two charged objects, or the two charges, right? So it's 20 millimeters, right? So now the possible questions we can expect here, it's obviously to know how to state Coulomb's law, right? So I hope everyone can state Coulomb's law, right? Because it just states very simple. It talks about the electrostatic force being directly proportional. And remember, this electrostatic force is being experienced by the charges, right? So you have to talk about that electrostatic force and talk about its relationship to the product of the charges, and also talk about the relationship of that electrostatic force. So I just want to take a look at the much more specific definition there when it comes to that one. So I think you would say here, it's question 7, of course. So they want us to state Coulomb's law. So 7.1, you'd say the electrostatic force. So I don't know, you can take the definition that you guys were given by your teacher. So, or you can take this one, the electrostatic force between two charged objects, right? So the electrostatic force between two charged objects is directly, so if you look at this formula, you'll see that FQ1, FKQ1, Q2, and then R squared, you can see that the force here is directly proportional to the product of the two charges. So by product we mean when we multiply the two amount of charges, we will get that it's directly proportional to the product, right? We'll get that the force is directly proportional to the product of those two charges, right? So we'll see that also the force here, it's inversely proportional to the distance. But remember, this is not just the distance, right? It's inversely proportional to the square of that distance, right? So here you can write that the electrostatic force between two charged objects is directly proportional to the product of the charges and inversely proportional to the square of the distance between their centers. Their centers, right? So there we have it, and that is the definition for Coulomb's law, right? But you can take the one that you feel is much more specific, or the one you were given by the teacher, right? So let's move on to 7.2, right? So on the second question here, they want us to calculate these electrostatic force that is being experienced the sphere X or the sphere Y exerts on sphere X, right? So remember, because these two charges are placed some distance apart, so the other charge is experiencing some electrostatic force due to the other one, and also this one experiences the very same amount of charge due to the other one, right? So let's now calculate this amount of force. Sorry, it's the force. So this experiences a force due to the other charge, and this also experiences a force due to the other charge, right? So let's calculate that force. So the force is equal to K Q1 Q2 over R squared, right? So you must remember man P, that man P would be just times 10 to the power of, so if you see MC, NC, right, you must remember that to do conversions here, when we want to convert this to coulombs, we must multiply by 10 to the power of negative 3, we must multiply by 10 to the power of negative 6, we must multiply this by 10 to the power of negative 9, and we must multiply this by 10 to the power of negative 12, right? So what we will do here is just to do the proper conversions here, and remember, this is just to convert the charges to the unit coulombs, right? So because these charges are given in nanocoulombs, we would select the right conversion there. So it means that when we see that 5, we will multiply by 10 to the power of negative 9, right? And the 8 will also multiply by 10 to the power of negative 9. So what it gives us there, it gives us the answers in coulombs, right? So now let's calculate the electrostatic force here, right? And remember, another hint that I can give you, I'll just erase this for now. When it comes to conversions, you must memorize that mm, cm, m, and km, right? So it means that here you must know how to convert to each bit between each and every single unit that is here. You must know how to play around this, right? I know that some students struggle with conversions, right? But here you would divide by 10, you would divide by 100, and you would divide by 1000, right? So here you'll just multiply by 1000, so you can copy this down, and then multiply by 100, multiply by 10, right? So let's now calculate the electrostatic force here. So remember, the distance there must be in meters, right? So we have the K here, the K value here, it's a constant. At the back of your formula sheet, you will see that you have Coulomb's constant, right? And it is the symbol K with the value of 9.0 times 10 to the power of 9, right? So charge Q1, we can say Q1 is 5, but then we must convert that to coulombs, so we would multiply by 10 to the power of negative 9, right? And then now we'll move on to Q2, we'll substitute 8. Remember, you don't put the sign when you're calculating the force, right? You don't put the sign, so it's going to be minus 9. So you're going to substitute all these charges as positives, right? Because you just want the magnitude of the charge. Remember, we're looking for the magnitude of the charge, right? And the signs only would tell us the direction of the electrostatic force of the specific charge, right? But now you'll just calculate the magnitude of that, right? So over, what is the distance here? The distance is going to be that 20 millimeters, and remember, because we're moving from 20 millimeters here, and the distance must always be in meters. So we'll divide by 10 and divide by 100, which is like dividing by 1,000. So let's just use the calculator there. So it's going to be 20 divided by 1,000. 1, 2, 3. And I think you will get that the answer is 0.02, right? Just wanted to make sure there, right? We'll get that the answer here at 0.0. Answer 0.02 squared, right? So let's calculate the force here, the magnitude of the force. It's going to be 9.0 times 10 to the power of 9, and then you multiply there. Remember, we had to do all the conversions here properly and make sure that the distance on the formula KQ1 and Q2, we make sure that the distance is in meters and your charges are in coulombs, right? So that's why we had to do all these necessary conversions here. And I think if you do that properly, and if I'm correct, your answer is going to give you 9 times 10 to the power of -4 newtons, right? So now let's move on to the third question, 7.3. So the 7.3 question says that we have to draw the electric field pattern produced by sphere X and Y, right? So because we see that this one is positive and this one is negative, so they will obviously attract each other, right? So if you draw in the field patterns here, you have it has to be symmetric. So the field pattern have to be symmetric, right? So you can see that here we've got 2, then I'll be forced to also have 2 here, then I'll have this, then if I have this, I can have something like this here, then I can also have this one here, right? But then now you can count, I think they are equally distributed here, and now these charges will be moving from the positive to the negative, right? So they're moving inwards on the negative charge, they're moving inwards and outwards, or they're moving outside the positive charge, right? You can see that they're going out there on the positive charge, right? So whereas on the negative charge they moving inwards, right? So I think that's perfectly fine there with the charges. We managed to do that. Then if it was positive and positive, you can also take a look at the book, but you will see that they will actually try to repel, right? They would repel, right? Meaning that they would try to repel. However, they would be going outside the charge. Do you see that? They'll just be going outside the charge, right? And stuff. So you have to obviously go back to your notes and take a look at how to draw these, right, for all those different cases, right? Because they can ask anything in the examination, right? So let's now go on to 7.4, right? So the 7.4 here, it's saying that the sphere Y is now moved closer and makes contact with sphere X, after which sphere X is repelled, right? So calculate the new charge here. So the new charge here, we would say the new charge, how many spheres did we bring together, or how many charges were brought together? 2 charges were brought together. So let's say Q1 over Q2, and then we divide by the number of charges. And then here we can choose to add the 2 charges, right? But remember, we must substitute the charges with their signs, right? So you see that it's a positive charge here, it's positive 5. We can convert, it's fine. So it's this charge, right? And then we're adding this with a negative charge, which is -8 times 10 to the power of -9 all over 2, right? And what is the answer here? So let's quickly add that. 5 times 10 to the power of -9 plus -8 times 10 to the power of -9 all over 2, right? So we'll get that charge here, the new charge. It's negative 1.5 times 10 to the power of negative 9 coulombs, right? So there we have the charge there, and I think we can now move on to the next question. So this is question 7, right? So in this question 7, we have to read the question carefully. So now question 7, we're given that point charges negative Q1, positive Q2, positive Q3 are arranged at the corners of a right-angled triangle, right? As shown in the diagram below, right? So I know that a couple of students struggle with this. I don't know why. Maybe it's because we have an anxiety of drawing maybe the free body diagrams here, because it's all about that. Should you do the proper calculations here, we know that it's just going to lead us to the Pythagoras theorem, but we will take a look at that, right? So state Coulomb's law. I'm not going to state that. You will either take the one that was provided by your teacher, or you can take the one that we just talked about here earlier in the video, right? So 7.1.2, draw a force diagram to show the forces acting on Q2, on the positive charge Q2, due to the charge. So we have to draw that force diagram, which is what I was talking about there. So the force diagram, or the vector diagram, we can draw it. So now, because this charge here Q2, because this force diagram, it has to be drawn on the charge Q2, right? We can place a point there, or we can just show the dot there, right? Because this is positive, imagine yourself as the charge, right? If you are this charge and you see someone positive or someone negative there, remember you are positive by that time. So if you see a negative charge here, you'd want to attract to that charge, right? And you see a positive charge here, which is this one, you would want to repel. Do you see that? So as a result, when you want to attract this, so this we can say this is force Q1 on Q2. So I will write F by it's force by charge number 1 on 2. So it's force by 1 on 2. So this is force by 3, right, on 2. Do you see that? So all these forces are being experienced due to the other charges, right? And they're being experienced by charge Q2, right? So now let's draw the vector diagram there. So the vector diagram here, it's going to be a dot, and with one force going up, which is this force is going to be due to or by charge 3 on the second on charge 2, right? And this one is going to be the force by charge 1 on charge 2, right? So your resultant force here, as a result, it's going to go to that direction, right? Which now we can talk about the direction, we can talk about the magnitude of the resultant force. Okay, for now, that's all on that question. That is the vector diagram drawn there. You have to imagine yourself as the charge and look at which directions you're gonna go due to the other charges, right? Good. So 7.1.3, calculate the magnitude of the net force, right? So the net force is the resultant force. So resultant force is the same as the net force, right? So let's calculate this net force. Because these charges are at right angled, because these two forces are at right angle with each other, right, as you can see there, it means that we'll have to use Pythag, right? But if these were on a straight line, then we would use the normal addition and subtraction, right? But because now they're at right angle to each other, or they're perpendicular to each other, we'll have to use Pythagoras theorem, right? So F net, it's going to be equal to F1 on 2 plus, so the square of this is equal to the square of that, F3 on 2, right? So we have to calculate each and every single one of these charges here, right? So that is the starting point. So let's start by calculating the forces of those charges. So force 1 on 2, it's going to be K Q1 Q2 R squared. So what is the charge here? 9.0 times 10 to the power of 9. And then the charge Q1, remember I said you will use man P, right? And if you use man P, you'll remember that times 10 to the power of negative 3 times 10 to the power of negative 6 times 10 to the power of negative 9. And because it's nanocoulombs, we'll have to multiply by times 10 to the power of negative 9, right, for the charge. So Q1, it's negative, so we just put it as positive. Don't forget that when we calculate the electrostatic force, we don't substitute the negative, right? Minus 9. And then the charge Q2, it's there, it's 4, so we put 4, it's this one. We put 4 times 10 to the power of negative 9, right? All over, what is the R squared? R squared will put the distance between the two charges, right? And remember, I think I gave you the conversion with that. So to move from meters to millimeters, we would divide by 1000, right? So you divide that 15 by 1000, you'd get that it's 0. Let's check it here. 15 divided by 1000, 15 divided 1000, we get 0.015 squared, right? So let's calculate the force here. So the force here is going to give us 9.0 times 10 to the power of negative 9, right? And times those two. Give you 3.2 times 10 to the power of negative 4 newtons, right? So that is the force experienced between those two charges. I have to quickly calculate the force. 30 on 2, right? So we'll quickly do that. It's KQ3 and Q2, right? Over the distance, the square of the distance between those two charges, right? So what is K here? It's going to be 9.0, right? 9.0 times 10 to the power of 9. Then what is Q3? Q3, it's charge 3, it's 5 times 10 to the power of negative 9. And then Q2, it's 4, we'll put 4 times 10 to the power of negative 9, all over, what is the distance between the two charges? It's 20 millimeters, so we'll put 0.02, square that, and then now we can quickly get the answer here. So the answer for this one, it's going to be it's 4.5 times 10 to the power of negative that. But now remember, the two forces we got here are representing these here, this one and this one over here, right? So they're perpendicular to each other, like I said, so we'll have to get the net force since the question is asking the magnitude of the net force. So we'll have to use F net. So the square of F net, it's going to be force 1 on 2 squared plus force 3 on 2 also squared, right? But because we're looking for the F net here, we're simply gonna put the square root of that, and then now if we put the square root, you will see that we will be substituting the actual values here, right? And this is squared plus 4.5 times 10 to the power of negative 4. It's also squared, right? So let's punch that quickly on the calculator to get the net force. So our net force is the square root of 3.2 times 10 to the power of negative 4. 4.5 times 10 to the power of negative 4. Okay, introduced to the square. So if everything is substituted correctly, and I think the answer is going to give us that it's going to be 5.52. Yeah, it's going to be 5.52 times 10 to the power of negative 4 Newton. So that is the magnitude of the force. So here they're not looking for the direction, but we do know where the direction is going. And if maybe they were looking for the direction, we would look for the angle, right? So I think it's perfectly fine there. We'll leave it here with that one, and we'll quickly move on to this question 11. So now let's do this question 11 quickly. So this question 11.1. So okay, let's take a look at this question. 2-point charges, right, Q1 and Q2, a distance 3 meters apart, are shown below. The charge on Q1, it's this amount, and we've got the charge on Q2, which is that amount. So we can see that Q1 has got this amount of charge, and Q2, which is Q1 has got minus 14 microcoulombs. So I think you can see that. The first question just went on straight and say we have to define the electric field at a point in space, right? So electric field at a point, it's usually defined by this formula here. So it is the electrostatic force per unit positive charge, right? So it is the force over the positive charge, right? So here you'd say that the electric field at a point, it states that the electrostatic force experienced per unit positive charge, right? Per unit positive charge placed at that point. So that is electric field at a point. It's the electrostatic force experienced per unit positive charge placed at that point, right? So 11.2 here, we have to draw the electric field pattern between the two charges, right? I think we've drawn this, it's negative and positive here earlier on the things earlier on in the video, right, for some of the questions here. So I think now getting familiar with this, if you didn't know how to draw this, right? But my advice is that please take a look at your notes in class, your grade 11 notes. You will see this, right? So like we said, these charges are just going to be moving outside the positive and into the negative, right? So they're moving inwards on the negative, right, and outside from the positive, right? So those are the field patterns there. So now let's move on to 11.3. Now they want us to calculate the net electric field at a point P, at point P, situated 2 meters from Q2, right? So let's do that quickly. So we have a point here. Remember, at a point is always positive, right? So this point acts positive, right? So now let's calculate the electrostatic force due to each charge here, right? So I am positive here. So if I'm positive, I see a negative charge this side, I will try to attract to the charge, right? So this is going to be E1 on P, right? So we're saying that this is the electric field by charge 1 on the point P, right? So this one here, it's positive. This charge is positive again. So due to this positive charge, it will also experience a negative, it will also experience a repulsive force, right? It will want to run away from the positive, right? So this one, it was trying to attract to that Q1, and on the other hand, it's trying to repel, right? So you may wonder, why am I writing this E2 on P small, right? The vector is being smaller than the E1 on P, right? So the reason I'm doing that is because remember, this formula to calculate the electric field, it's KQ over R squared. And remember, the greater the distance, the smaller the electric field the charge is going to experience, right? So by a bigger vector there, or by this big arrow here, I'm indicating that this magnitude it's greater. So the magnitude that it experiences due to charge 1, it's greater than the magnitude it experiences due to charge 2, because of the of the distance, right? Because it's closer to charge Q1, but it's far away from charge Q2, right? So this is 1 E1 on P, right? So let's draw E2 on P. So it's going to be smaller than that, E2 on P, right? So now let's quickly calculate the electric field. So it means that the net will obviously be going in that direction, the E net, right? So we have figured out the direction of the E net, right? But to get this E net, we have to get E1 on P first. So how do we do that? We say KQ over R squared. Then what is K? K is the charge, is the Coulomb's constant, right? It's over there at the back of the formula sheet. So Q, it's the charge, which is 14. And remember, we don't substitute the charge here. We don't substitute the sign. And because it's because we're going to use man P, and this U has got minus 6 in it. So this is minus 10 to the power of 3. This is 10 to the power of negative 3. And then this is 10 to the power of negative 6 and 10 to the power of negative 12. 9 and 12, right? So here we'd use negative 6, right? All over the distance. What is the distance between that and that? So because we have the total distance here, all the way from here to here, which is 3 meters, and to work out this small distance here, because we must substitute the distance from the charge and that point that we are calculating its electric field for, right? So we look at the charge and the point. So the distance here is going to be 3 minus 2, which is 1, right? So the distance here, if you pay attention, it's just 1 meters, right? So we'll go and substitute that as 1, then we square it, right? So let's punch on the calculator and get the answer. 9.0 times 10 to the power of 9 times 14 times 10 to the power of negative 6 all over 1 squared. So it's 120. So it's 126,000. 126,000. And remember the SI units here. If you forget the SI units, you would look at the formula at the back, and I think there's Newton and the charge is in Coulomb. So this is Newton per Coulomb. I'll write it like this. So don't forget the SI units, don't write newtons only. So let's get E2 on P. So E2 on P would say K, the charge over R squared, right? So here, what is the K? 9.0 times 10 to the power of 9. And what is charge Q? The charge Q, it's going to be Q2 now, which is 20. 20 times 10 to the power of negative 6, right? Because it's negative 6 here, the U, right? So all over the R, and remember the distance between the point and the charge. So the distance between the point and the charge, it's simply just 2 meters. So we'll put the 2 there, substitute the 2. No need for conversions because the distance is already on its SI units, on its correct SI units, right? So let's quickly go and edit this on the calculator to see what is the answer. So we'll see that here we'll get an answer that is going to be 45. It's 45,000. So that is the electric field, right? And I think you can agree with my observation over there when it comes to the magnitude. By the time I was indicating the vectors, I mentioned something important, that in terms of magnitude, the E1, it's going to be greater than the E2 because of the distance, right? The separation. So the closer the point is to the charge, the greater the electric field it will experience due to that charge, right? So let's now calculate the E net. So to calculate the E net here, would say E net is equal to the sum of those two, because they're on the straight line there. We can see them clearly there on the vector diagram, right? So it's going to be E1 on P plus E2 on P, right? And I think it's going to simply be 126,000, because they're going in the same direction. We're taking that direction as positive and this direction as negative, and then we will add them. It's 45,000. So no need for Pythagoras theorem here, because these two are not at right angle to each other, but they are simply parallel to each other. So we'll simply add or subtract them, right? Because they're going in the same direction, we'll simply add them. And I hope you would get that the answer is 171,000, right? So I think with this video, it's just gonna end here, because we've obtained the net electric field that is being experienced at point P, right? So please, you must be able to do these kind of questions. So at a point is always positive. Then when you look at in relation to the other charges, this can help you figure out the direction of the charge, right? So let's take a recap here. This charge was positive, so due to Q1, it will try to attract to Q1, and Q2 due to Q2, it will also try to repel, right? Because it sees a positive, right? So we can specify that this is E1 on P and this is E2 on P. So that's how we draw the vector diagram or the free body diagram. We take a look, we imagine ourselves as the charge and take a look at the possible directions that we will go into, right? And as a result, the E net would be going to the left, right? If they ask even direction next time, we can specify it. I think you've learned quite a lot on this video, and I think I will take the opportunity to end this video here, and I would like you guys to make some comments and let us know what you guys think about this, and we will see each other. And I hope you would have learned a lot of ideas in the videos, and if there's any mistake or anything that you would like to share with us, of course you can mention that on the comment section. So I think it's perfectly fine with this video, and bye.